Hello, student. Today we'll be looking at stress and strain, and it's part of the topic for the syllabus under theory of structures. And under this topic, we'll be looking at the following subtopics. We'll look at what is direct stresses, Young modulus, the stress-strain curve, factor of safety, Poisson ratio, composite bars, temperature stress in composite bars. Let's start by defining what is direct stresses. Direct stresses can be in form of compressive and tensile. And as we are seeing on the screen, for example, let's say you have a bar of material and it is being pulled apart with a force F. Then the internal stress that would develop inside that bar is being referred to as a tensile stress. But in the case of the forces being compressing the bar, in which case the bar is being compressed and the internal stresses developed will be the compressive stress. Generally, the stress can be analytically defined as the force over the area. So the direct stress can either be a tensile stress or a compressive stress, which is the direct axial force divided by the cross-sectional area. The direct stress can cause lengthening if it is in tensile, but if it is in compression, you will realize that the bar will be shortened. Strain, in the other hand, is the ratio of the change in length, because when a force is being applied on a material, there is tendency that the material fails after some time. And in that case, it's either the material has increased in length or the material has shortened in length. So there will be a change in length. So the ratio of the change in length and the original length of that material becomes our strain. So that is what you see in there. And whereby the Young modulus is the relationship between the stress and the strain. So the ratio of the stress and the strain is what we refer to as the Young modulus. This graph is showing an example of a failed material. Let's say, for example, a mild steel. But before a material fails, it goes through different stages. The first stage is what we call the elastic limit stage. At this stage, the material increases, and there is a linear relationship between the stress and the strain. That is, as the load is being applied on the material, the change in length is equivalent, is directly proportional to the strain observed. So in that case, at that point in time, the material is within the elastic limit, meaning that when this load, when the stress is being removed, the material can return to its original shape. That means the material will not deform. It has not deformed, and there's no change in length. At that point, we have the material intact, even when the load is being removed. But it gets to a point along the line as stress increases. It gets to a point where we call the yield stage. At that stage, you see an increase in strain. So the relationship between the stress and the strain is no more linear once it gets to a yield stage. So at that point, any increase in stress, we have an higher increase in strain. So when we start observing that the material has got to that stage of yield, and once the stress continues, as in the load continues to increase, it gets to a point whereby the material becomes plastic. So at that stage, increase in stress gives a greater increase in strain. Then at that point, from the yield stress point, if the material the load is removed from the material, the material will not come back to its original position or the original shape. So at that point, deformation starts at the point of yield. But as it continues, it becomes plastic, whereby we have large deformation being observed in the material. So when the stress increases, we have greater increase in strain. So at that point, you have the material getting towards failing, and it continues like that. As you increase the stress, you have greater increase in strain when it is within the plastic limit region. And again, it continues until the material finally fails. And at that point, it becomes the point of fracture. And the slope of the graph within the elastic limit is the Young modulus, which is the ratio of the stress all over the strain. Now, what is factor of safety? Remember, we said looking at the graph, at that elastic limit, the material is still working under normal condition. At that point, there is a directly proportional relationship between stress and strain, and the material has not deformed or has not failed or has not shown any sign of deformation. Within that limit, within that point, that is when we have the working stress. The working stress is a stress at which the material is under the normal working condition. But once the material gets to the yield stage, that is when the deformation starts. That is when we start seeing deformation in the material. So at that point, what happens is the yield stress. So we said the yield stress is a stress in which the material begins to deform plastically. So at that point, any increase in stress will give a greater increase in strain, whereby the stress factor is now the factor against yielding, which is now the ratio of the yield stress to the working stress. So the stress factor is the ratio of the yield stress all over the working stress. Poisson's ratio. Now, when the material deforms, and at that point, then we can say, okay, there is a strain that can be calculated because now we have the extension all over the total length. But then it depends on the direction at which the deformation is being calculated. If the strain is being calculated in the direction of the applied force, then the strain is being referred to as the longitudinal strain, or what we call the axial strain. But if the strain is being calculated in the other direction, which is not directly the direction of the applied force, then it is the transverse strain or the lateral strain. And the Poisson's ratio now is the ratio of the lateral strain to the longitudinal strain. And it can be written in form of a ratio 1/m, where m is a constant. So now you have the ratio of the lateral strain to the longitudinal strain. Remember, the longitudinal strain is a strain in the direction of the applied force, whereby the transverse strain is a strain in the direction that is not of the applied force, so in the opposite direction. So then the ratio. The Poisson ratio is now the ratio of the lateral strain to the longitudinal strain. Now, coming to composite bars. Now, generally, when you talk of a structural unit, some of the time you realize that the unit is a combination of different components being put together to form a single unit. And in such cases, sometimes you have different materials being used to create a certain unit. So when a bar is made of two or more different materials and is being connected together or is being put together as a unit, then that bar is said is a composite bar. And so a composite bar is when you have bars that are made of two or more different materials, and these bars are connected such that the change in length under load is the same for each constituent material. So the material is connected as a one unit made of different materials, and they are connected such that when there is a deformation, the materials deform together, they deform in the same manner. So, and the total load on this material will be shared by each of the constituent member. So the total load on the composite is the sum of the load carried by each of the constituent member. So, and the strain will be the same because they've been connected and joined together. So the strain will be the same, and because they deform at the same magnitude. So the strain is the same. So just note that when you are dealing with composite bars that are connected together, there are things that you just have to understand, that these bars have the same strain, they deform in the same manner, but the load that is being that this bar is being subjected to will be shared by the different materials, by the different constituents that made that bar. So based on that understanding, we can now come up with some certain equations such that we say P, let P represent the total load on the composite bars, and let C and S be symbols for different material. So the total load on the composite bars will be the load on material C plus the load on material S. And the strain will be the same. Remember, our strain, looking at that equation of the Young modulus, remember the Young modulus is what? The stress all over the strain. So now, making the strain the subject of the formula, in this case, the strain becomes your stress all over elastic modulus. So the strain for each of the material will be the same. So the strain in this case is the stress of this material C over the Young modulus of the material C, which should be the same as the stress of material S divided by the Young modulus of material S. And now we can, from these two basic understanding, other mathematical equations can be derived, such that already we know that stress is force over area, the load all over the area. So in that case, if you want to make the load the subject of the formula in terms of stress and area, it becomes the stress multiplied by the area. So in the case of the load at C, we can convert it in terms of stress and area to say it is the stress of C multiplied by the area of C. In the case of the load of S, we can convert it to be the stress of X multiplied by the area of X. So and so on, you can have different mathematical equations depending on the problem you are solving at the time. Now, let's now assume that the bars are not knitted together, are not connected by force together, but they are being arranged in such a way that the arrangement is in series. So when the bars, the composite bars are being arranged in series, then it becomes a total different scenario compared to when the composite bars is being connected, knitted together. So in the case whereby the bars are being connected in series, just like we see in this figure now, bar A of material A and bar B of material B is being connected in series. So in that case, the force that is being applied on this material will be the same force that will pass through both bar A and bar B. So the total force will be the same force that will pass through bar A and the force that will pass through bar B. And because these bars are not connected, knitted, joined together, they are arranged in series. So the change in length will be different for each constituent member. So the change in length under load is different for each constituent bar. So A, we have its change in length, and B, we have its change in length, such that the total change in length will now be the sum, the addition of the change in length of A plus the change in length of B. So in this case, the mathematical equation will be different from the case whereby they have been connected together without any allowance to deform separately. So in this case now, we say the total force will be the force in material A and the force in material B is the same. So the total force passes through material A and also material B of the same magnitude. So the total force is the same force in material A and the same force in material B. But now, because they have the opportunity to deform differently in this case, so the change in length of material A is different from that of material B. So the total change in length will now be the addition of the change in length in material A plus the change in length in material B. So you have to understand that when you have solving a problem, you have to first understand what kind of composite bar is this and in what way have they been arranged. So if they are arranged in bars, then it gives you a different scenario than being connected together. Now, another thing that happens between composite bars is what we call the temperature stress, such that when there is a change in temperature, either it is being increased or decreased, it affects the stress that takes place within the bar. So, and again, remember this in case of composite bars, the bars are made of different materials, so they behave differently when they are subjected to temperature change. So the materials don't have the same coefficient of thermal expansion. So that affects the way they behave in the case of temperature changes. So the internal stresses are set up by temperature changes in a composite bar made with materials of different weight of thermal expansion. So if you have two materials of two different properties in terms of the coefficients of the thermal expansion, they behave differently, during temperature changes, and this will affect the whole composite. And how that is what we are going to look at now. If the bars, let's say A and B, are separated, each bar will extend separately. So if you have a composite bar and the bars are not connected together, if they are separated, so in that case, they had to expand differently because now they have different of thermal expansion. So now, what are the things that we need to take note and that will be needed in this case is that for a bar A, for example, the extent of deformation or the extent of changes that will happen based on the temperature will be the coefficient of thermal expansion of that material multiplied by the original length of that material and the change in temperature. So either it is increase or decrease in temperature. And then for material B will extend by the coefficient of thermal expansion of that material, the original length, and the change in temperature of that material. I hope you are following. So, the extent of expansion will be in that manner for each of the material. So now, if the bars are not joined together, so they extend separately with that magnitude, they extend separately. But if the bars are joined together, under increased temperature, for example, now, the bar with the higher coefficient of thermal expansion, we extend more originally, and the one with the lower coefficient of thermal expansion, we extend, but not to the extent of the one with the higher one. So now, because they are joined together, there is no way the deformation can be separated. So what happens internally is that the one with the higher coefficient of thermal expansion, because it has a tendency to extend more. So there will be a force that will compress it by a force F. So by a force, it internally compressed by that force F, whereby the one with the lower coefficient of thermal expansion will be extended by that equal force F, so that both of them shows the same increase in deformation. So if the bars are joined together under a lower temperature after compression, because now when it is being lowered, the one with the higher coefficient of thermal expansion will decrease more than the one with the lower coefficient of thermal expansion. Yes. So in that case where the temperature is being lowered, there is an internal force that will now extend the one with the higher coefficient of thermal expansion, and that equal force will be used to compress the one with the lower coefficient of thermal expansion, such that the material shows the same magnitude of deformation at the end of the day. So what I'm saying is that when this composite bar is being subjected to temperature changes, either by increased temperature or lowered temperature, it affects the internal behavior of the composite bars. And the stresses that takes place internally is what we refer to the temperature stress. And if the materials are subjected to increased temperature, the one with higher coefficient of thermal expansion will be compressed by a force F, and the one with the lower coefficient of thermal expansion will be extended by that equal force F. And if they have if the composite bars are subjected to lowered temperature, the one with the higher coefficient of thermal expansion will be extended by a force F, whereby the one with the lower coefficient of thermal expansion will be compressed by an equal force F, such that if the coefficient of thermal expansion of material A is greater than that of material B, the total extension, which is the addition of the two, will now be for material A, which has been extended, extended plus, and the effect of that of the material B. So remember, when we say if they are separate and they are not joined, separated and they are not joined together, they extend differently with the magnitude of a coefficient of thermal expansion multiplied by the original net and the change in temperature. So the total extension will now be the effect of the change in material A minus the change in material B. Let's see what we are saying with these diagrams. For example, the first case is talking about, this is the bar. We have the bar, we have the tube, which are now composite bars, and they are connected together. So when this temperature is raised, let's say by 3 degrees Celsius, then Material B, which is the bar, let's represent it by B, and the tube, let's represent it by C. So, and the material B has a higher coefficient of thermal expansion than the tube. So what happens is, because the temperature has been raised internally, bar B extends more. That's what we're seeing here. It extends more than the tube. The tube also extends, but not as much as the bar. So now, for this material, because they have been connected together, and they cannot extend or deform separately, there will be an internal, there is a internal force that is being applied, such that it will force material B to compress and force the tube to extend, such that the two are now at the same level, of extension, because they are being forced. So the same force F being applied on the bar, which compresses it, will be the force F, which extends the tube. So at the end of the day, because they have been connected together, the extension will be the same. But before they are the same, remember there is that internal force that has been applied, internal stress. So that is why you see that arrow to show this is compressed and this has been extended, such that they are now on the same level. So the total change in length in this case will be the change in length, original change in length of the bar B, minus the change in length of the tube. And that is what we're trying to explain with this equation. So the extension of material, the first material, minus the effect of the extension of the second material. But in the case whereby the temperature is lowered, and now in this case we represent the materials to be A and S, such that the coefficient of thermal expansion of material A is greater than the coefficient of thermal expansion of material S. So when the temperature is being lowered, material A tends to decrease more than material S. Both of them decrease, but then because of the different coefficient of thermal expansion, material A is being affected more. So it decreases more than material S. But because they have been connected together, there will be a setup internally such that a force is being applied on material A to force material A to extend, while material S to compress. And both of them are now at the same level of extension because they have been connected together. So material A is extended by a force F, and material S is being compressed by a force F. So that is just a summary of what we'll take today on stress and strain. But we can look at some examples. And I will just go through these examples. If you have questions, just take note of your questions and send me an email with your questions, which I will answer. And you can also discuss your question under the discussion forum on my UNISA. So let's look at this example one. It said a steel rod of that diameter and that length is encased by a cast iron sleeve of this thickness and of internal diameter of that. The assembly is subjected to a load of 40 kilonewton. Find the stresses in the two materials and the elongation of the assembly, and the Young modulus of each of the materials are given. So in this case, the first thing, before you can solve any problem is for you to understand the problem. Once you understand the problem, then it is absurd, because now you can based on your understanding, can now try to solve the problem. But in this case, we have two materials. We have the steel rod and we have the cast iron. And it's been stated that this material, it's been stated that the steel rod is being encased by the cast iron. So that means these are composite bars that have been connected together because it's been encased in that cast iron. And then the dimensions are given and how it's been encased is given. So now, when you have a composite bar that are connected, there are things firstly that comes to your mind. You know that this material have a force. In this case, we are given the load at which they are being subjected to, and that is the total load of P. And when they are connected in that manner, we know that the load will be distributed, to the two material. So the total load will be the load on the cast iron and plus the load on the steel. So for the cast iron, we're represented by C and the steel by S. And in terms of stress and area, we can convert this load to stress multiplied by the area. So you are forming your equations that will help you to solve the problem. So the first theory is the load is the total load, which is represent the load on each of the material being put together. And we represent that in terms of the stress and the area. And again, because they have composite bars that have been connected together, the strain is the same. So the strain in the cast iron is the same as the strain in the steel rod. So we have these equations. So with this equation, we'll be able to solve the problem. And again, you also have to understand the arrangement of this material. Remember, the steel rod is encased. So that means the steel rod is inside the cast iron. So the cast iron has a sleeve of 8 millimeter, and that it has an internal dimension, a diameter of 60. So, and the steel rod also has that diameter. So that means the steel rod fit inside the cast iron, which has that sleeve of 8 millimeter thick. So, the first thing the question is now we want to get the stresses in each of this material and also to know the elongation of their assembly. Okay, so how do we go about it? What do we know? What do we have? What parameters do we have that can help us? Because sometimes you have to understand what are the given parameters. And within the given parameters, you'll now be able to apply your equation to get to what you're actually looking for. So we have the diameters and the dimensions and all that. So from that, we can get the area of each of the materials. So the area of the steel will be pi d squared over 4. And in this case, the diameter is 62. We calculate the area. The area of the cast iron will be the total area, because now remember, the 60 is encased, diameter of the steel is encased inside, and the sleeve has an 8 millimeter thickness. So in total, if you look at that, the total diameter of the whole assembly will be the 8 millimeter thickness plus the 60 plus the 8 millimeter. So in that case, we get 76. So it will become the total area minus the area of the steel that is encased inside it. So to get the total area of the cast iron, it is the area, the total area, pi d squared over 4 minus the area of that space that the steel is taking. So in that, we have the total area of the cast iron. So now that we know the area and the total load has been given to be 40, we can apply equation 2, whereby you have the total load, the area, and the area of cast iron multiplied by the stress of cast iron plus the total the area of the steel multiplied by the stress of the steel. So this gives us an equation, and we can name it equation 4, such that we have the stress of cast iron and the stress of steel as the unknowns. Okay? Then what other thing can we apply? Another thing we can apply is that the strain is the same for both materials, and the Young modulus for each of the material has been given. So we can apply equation 3 to form another equation. So now we come to equation 3 and we put the value of the Young modulus for the cast iron and that for the steel, and that gives us what we have here. So when you do that, you get another equation whereby the stresses are the unknowns. So now we have two equations whereby the stresses are the unknowns, and two equations, two stresses, then it becomes easy. We can use our simultaneous equation to solve the problem. And using the simultaneous equation, you get the stress in the steel and the stress in the cast iron. So that settles the first aspect of the question. The second aspect of the question, it says that we should get the elongation of the total assembly. Remember that because they are connected together, the strain is the same, then the extension will also be the same. So we can decide to use, we can decide to use any the information of any of the material to solve this problem, because the strain is equal to the change in length over original length, which is in terms of stress and Young modulus is the stress over Young modulus for each of the material, and it is the same. So in this case, we've applied the one for the cast iron, because now our interest is to know the change in length, which is the elongation. And if you now take that equation to say change in length over original length is equal to the stress of the cast iron divided by the stress of the by the Young modulus of the cast iron. So we can now make the change in length as a subject of the formula. Then we put the values, because already we know the stress of this material, we know the original length which is being given in the question, and we know the Young modulus. Then we get it. You can also try and use the values for the steel rod and apply it. You realize that you still get the same result for your elongation. Okay, so in the second question is similar in approach, but in this case you have a concrete column, and which is this 50 centimeters square, and the reinforcement, you have 4 reinforcement rods at of each of 2.5 millimeters centimeter diameter for each of this rod, which is embedded inside the concrete. So by the time when you call the cross-sectional area, you realize that you have your column with the 4 reinforcements being there at the corner with that diameter. So he said it is being embedded in the concrete near the corners of the square. If the Young modulus of the steel is this amount, and that of the concrete is this amount, estimate the compressive stresses in the steel and concrete when the total thrust of the column is 1 meganewton. So now we have the diameter of the rod, and we have the dimensions of the column, because the column is a square column. And then we have their Young modulus, and we have the total load. So having these parameters, knowing that these are the parameters we have, and we are interested in getting the stresses and on each of the material, it's still like the first example. It's just a concept that the question is different, but the concept is the same. So you just apply the theory, which is that when a composite bar is connected together, their total load will be shared within the two materials, and which can be written in terms of the stress and area, and the strain will still be the same. So we still apply the 3 equations. So, but in this case, what we've done is that we've just, before we even start solving the problem, we worked on the equation, mathematically, in any, just to make the stress the subject of the formula. So from equation 3, you can have this to give you equation 5. The same thing from equation 3, you have this to give you equation 4 and equation 5. From equation 2, you can make the stress the subject of the formula to give you another equation 6. You make the stress of the steel, the sort of the formula to make equation 7. So it's still the same as what we've done in example 1, but in this case, we worked on the equation first before solving the problem. So now, looking at equate equation 4 and 6, because now equation 4 talks about the stress of the concrete, equation 6 talks about the stress of the concrete. So we can equate them together because they both represent the stress of the concrete. So when you equate them together, you have a general equation that can solve the problem of the making the stress of the steel the subject of the formula. The same thing if you equate equation 5 with equation 7, because they both talk about the stress of the steel, it gives you a final equation. So in this case, what we just do to get the stress of the compressive stress on the steel, then you have the total load which has been given. You get the area of the steel which can be calculated. You get the area of the concrete which can be calculated. The Young modulus of the concrete which is being given, and the Young stress of the steel based on the equation 4 and 6. And we have equation for the stress of the concrete based on equation 5 and 7. We can apply these equations to calculate the stresses of these materials. So our interest is just to input the parameters. And what are those parameters? The load which has been given, the area of the steel and the area of the concrete which has been given, or which can be calculated. Of course, we have the dimensions, but we can calculate the areas. And we have the Young modulus of the concrete which has been given, and the Young modulus of the steel which has been given. So now, the first thing is to calculate the cross-sectional area of the steel. Remember, we have 4 of these steel being embedded in the concrete. And because they have 4, we also get the area of those 4. So the area of 1 is pi d squared over 4, putting the diameter, multiplied by the force, showing the number of that steel embedded. So, and to calculate the area of the concrete, remember these steels are being embedded inside the concrete, so we calculate the total area, then we subtract the area of the steel that are embedded in the concrete, and that is what is being done here. It's a square column, and it's a square concrete column, so the area will be breadth, length times breadth, which is 0.5 all squared, minus the area of the steel, and that gives us the total area of the concrete. So now that we have all the parameters for those 2 equations, then we can just input those parameters into the equations, and we'll be able to get the stress in the steel and the stress in the concrete. So whichever method you decide to follow, either to follow the method being used in equation 1, example 1, or you use the question being used in this example 2, is the same. It's just, but the major thing is for you to understand the concept. Once you understand the concept, then whatever way you go about it, you will get the correct answer. So let's look at the next question. The next question says a bar of steel having a rectangular cross-section of these dimensions carries an axial tensile load of 180 kilonewton. Estimate the decrease in the length of the side of the cross-section if Young modulus is this, and if the Poisson ratio is given to be this. And remember, I said the first thing you want to do is that you try to understand the question, because once you understand the question, you'll be able to solve it and apply the relevant equations to it. So what are we looking for in this case? We are looking for the decrease in length of the sides, of that section. And then when you talk about of decrease in length, we are actually looking at the strain, because the strain is the change in length, is the ratio of the change in length to the original length. So the first thing we have to do, we have to get the strain, which is a longitudinal strain. And then to get that, we calculate the area of that cross-section, because the rectangular cross-section, so it is the length times breadth, so we multiply, then we get that area out. Then the stress of that will be force over area, because we were given the force. So before we can get the strain, we can't just get the strain directly. directly, but we have to check the parameters that are given and look at how can we get into what we are looking for. So in this case, because we have the Young modulus, we have the total load applied, we know the area. So once we get the stress, and with the Young modulus, we can easily get the longitudinal strain. So now looking at this, we have the longitudinal stress to be force over area. The total force is given and the area has been calculated, and that gives us the stress. Now, having known the stress, we can easily get the strain. The strain is stress over Young modulus. So we put the values of the stress divided by the Young modulus given, and that gives us the longitudinal strain. Remember that longitudinal strain is a strain along the applied load. So it is in the direction of the applied load. And in this case, our interest is to get the decrease in length of the sides. So now we are interested in knowing the lateral strain, along those sides, and the Poisson ratio has been given, so it makes it easy. Remember, the Poisson ratio is the transverse strain over longitudinal strain. And now that we've known the longitudinal strain, then the transverse strain on each side will be the Poisson ratio multiplied by the longitudinal strain. And that is what has been applied here. So the lateral strain will now give us the Poisson ratio multiplied by the longitudinal strain, and we have that as the lateral strain. So let's take it side by side. Because we have the 7.5 centimeter side and we have the 2.5 centimeter side. So if you want to know to what extent will 7.5 centimeter side contract, remember strain is what? Change in length divided by the original length. So to know the change in length, in this case, it will be the strain, which is now the lateral strain, multiplied by the original length, which is 7.5. And that is what is being done here. And this has been converted to meter. So we have it to be 0.075 multiplied by the lateral strain. And that gives us that. So this side of the cross-section contracts by this amount. And in terms of the side of the 2.5 centimeter, it's also the original length, which is now in this case 2.5 multiplied by the lateral strain, and that gives us the value at which that side contracts. So that is that. So the thing is, once you know the theory behind it, you understand the concept, you'll be able to apply different equations and understand different facts into your equations, into your problems, and you'll be able to get the solution. Now, let's look at this last one about the temperature stress. Remember, we said when we have a composite bars, and these bars are subjected to temperature changes, either increase in temperature or decrease in temperature, it affects the behavior of the composite bar. So let's look at this example. An aluminum rod of 8 millimeter in diameter and 30 millimeter long is joined to the end of a steel rod 5 millimeter in diameter and 60 millimeter long. The composite rod is then heated through 120 degrees Celsius. Now we are expected to do the following calculation. But before we go to that, I want to remind you that, remember, composite bars can be connected or binded together or can be arranged in series. So you have to be careful to know, is this one connected together or is this one arranged in series? Because the way at which they've been arranged will affect the way it will be calculated. So in this case, now, it said we have this aluminum rod, which has been joined at the end. It said the diameter and this long is joined to the end of a steel rod. So that means the connection is in series. And remember, when the connection is in series, they expand differently, such that the total expansion will now be the addition of the expansion of individual material. And if they are arranged in series also, the load or the force is being transferred through the material. So the loading transferred in material A is the same load in material B. I just wanted to remember that before we go to the calculation. So the A part says, calculate the total increase in length of the composite bars if the composite rod was allowed to expand an amount of this. So let's say it's allowed to expand during the 120 degrees Celsius temperature change. What stresses will be set or calculate for the above the final position of the junction between the two materials after the change in temperature. So we take it after the change in temperature. We take it one after the other. So the arrangement looks like this. This is being attached to the end of the steel with those dimensions given. And because they are arranged in series, so the total change in length will be the addition of each of them because they expand differently. And now, in terms of temperature, the change in length will be the coefficient of thermal expansion multiplied by the original length and the change in length for the aluminum A, and that for aluminum B will be the total change in length. So now, because we have all the parameters, to calculate the total change in length, we know the coefficients of these materials, we know the total length of each of the materials, and we know the temperature changes that they've been subjected to. So easily from here, we can calculate the total change in length. So we have put in those parameters and we get the total change in length answer. So the next question in B says that if the composite rod was allowed to expand by that amount, so there is now an expansion that is being allowed. You get it now? So it said if it is allowed to expand by only, so we are not now looking at the change in length or the free change in length. Now it's being constrained. So we say it's been allowed, to expand only by 0.15 millimeter. Then the composite bars must have been contracted. Because now, if the total expansion is supposed to be 0.166, and it has been arranged in such a way that it can only be allowed to expand by 0.15. So that means internally there must be a kind of contraction that has taken place such that the composite bars has been contracted by that difference. So it's 0.166 minus the 0.15. So there must be a contraction of this internally to be able to make the composite rod to only expand for the amount of 0.15. So in that case, we apply our equations. Remember, we have the total expansion to be this for A and that for B, the addition together. And this can also be expressed in terms of stresses. Because now the questions that we want to deal with says what stress. So remember, because depending on what you are looking for, then it will determine how the equation that will be applied. So we are interested in getting the stresses. So of course we have to write our equation to have stresses involved. So it will have in this case, the change in length can be written in the form of length multiplied by the stress divided by the load modulus. Where do we get this from? Remember, the strain is what? Change in length divided by length, by original length. And strain, again, it is stress over Young modulus. So if you put together the equation of the change in length divided by length to be equal to stress divided by Young modulus, and you make the change in length the subject of the formula, you will realize that the change in length can be written in terms of original length multiplied by the stress divided by the Young modulus. So we get that equation from that. So now we will be applying this equation, believing that the material has been subjected to a contraction of 0.016 millimeters. So we apply this. So now we have an equation because now we have two unknowns, the stress in in A and the stress in the steel, the stress in the aluminum and the stress in the steel. So now we have this equation. We can't go further. It becomes our equation 1. So next thing we'll think about is, okay, what else can we do to be able to solve this equation? Because now we have 2 unknowns in one equation. So we have to look for other equations so that we can be able to solve the stresses. So another fact that we think about is that when composite materials are arranged in series, the load or the force, is passed through the materials in the same manner. So the force in the aluminum is the same force in the steel. So we're going to apply that. And this force can also be written in terms of stress. Remember, stress is what? Force over area. So force can be stress multiplied by the area. So we prove that the stress of A, the area of A is equal to the stress of B and the area of B. So we put the stress as the subject of the formula of A, and already it's easy to calculate the area because we know the dimension. So we calculate the area of the aluminum, we calculate the area of the steel. So we put those parameters, and we're able to have another equation with 2 unknowns. So now we have 2 equations with 2 unknowns. Having 2 equations with 2 unknowns is now very easy to solve simultaneously, and we're able to get the stresses in both the steel and the aluminum under the condition that the material will not be allowed to extend beyond 0.15 millimeter. So now the last question there says that we should calculate, now referring to B part now, we should calculate for B the final position of the junction between the 2 materials after the change in temperature. Remember, because they extend separately, so the final position of the word will be the new length or the new length of aluminum. Because we are talking of this junction, what will now be the final position of, after they've been extended to that amount, what will be the final position at this their junction? So the final position will definitely be the position of the aluminum, the new length at which the aluminum has extended. So what we are actually looking for will be the extension for aluminum. So we say, considering aluminum to get the final position of the junction between the 2 materials, the free expansion of aluminum, as far as temperature is concerned, is coefficient of thermal expansion multiplied by the length and the change in temperature, and we have put that. And due to stress, because remember, it's been subjected to change in temperature and also subjected to load. So due to stress, the change will also be, just like I've explained, that we can write the change in length in terms of stress and modulus and original length. So we use this equation also. So due to the free expansion, we have that values as the aluminum has expanded according to based on the temperature changes, and due to stress, we've been extended to this. So aluminum extends will be based on the 2 extension now. It will be the extension based on the temperature changes minus the expression change due to stress. So the aluminum extends by this value. So if aluminum extends by this value, the new position aluminum will be that extension value plus the original length, because now the length of the aluminum is this, then it has extended by that value. So the new position will be somewhere around there. So now the new position of aluminum will be the length of the aluminum plus the now change in the length, as in the extension that the aluminum has extended. So we add it together to get the new position of the aluminum. And that will be the new position of the junction between the 2 materials. So this is how far we can go on this topic. There are other exercises that you can see in your study guide, even in other textbooks, that can help you to expand your knowledge of this. Remember, this is a calculation module, so the more you practice, the more you understand, and the more you'll be able to apply the concept that you have acquired. And if you have any questions, please send me an email with your questions, which I will answer. And you can drop some of your questions in the discussion forums on my UNISA so that other students can also see and also comment on your questions. So I wish you best of luck. We'll do other videos for other topics also. Thank you.